Welcome back, guys. Here is our fifth subunit on the topic numbers. In this topic, we'll be discussing rates, ratios, and proportion. Once again, I want to say this topic is taught in the lower school. And so in this class, we are merely reviewing the key concepts that we need to take care of in this area, right? So this is not like a new topic. It's just review in order for us to be able to handle the topics that are coming up that are relevant to this class, okay? So part one of this discussion is on rates. Second part will be on ratios, and then we'll complete with proportions. We will also then consider the three of them together with a discussion on percentages, right? So this should hopefully take a very short time. This particular lesson should take us even shorter because rates are relatively easier, especially when we think of unit rates. Okay, so let's get started. The discussion on rates, ratios, and proportion is really a discussion of problem solving. We want to sharpen our skills in the process of problem solving, and this is, in fact, is the reason why it was important we look at this, okay? So how do we normally solve problems in mathematics? What are the steps to follow in order to be successful when we meet a problem and when we go into the process of solving it, okay? All right. So, for example, I want to start this by using, an opening problem. Sama's reaction time when driving was measured to be 0.85 seconds. How far would her car travel in this time if the speed of the car is 82 kilometers per hour? Okay, so this is a typical rates problem. But let's understand what exactly we are talking about. So when we want to solve a problem such as this one, what are the steps to follow to successfully arrive at the correct answer? All right, so we want to be able to, and now I'm listing the kind of steps that I want us to be thinking about. There are going to be 6 of them that to think about carefully. So the first thing is we want to read the question carefully. All right, so if you're given the question like this, spend a few minutes to read and be sure that you understand what the question is asking about, right? What the question is about. Okay, secondly, we want to ensure that we know what we are being asked to do. For example, in this question, we're being asked to find how far the car travels in 0.85 seconds, right? So how far does the car travel? That means what distance does the car travel in during the reaction time, okay? The next thing we want to do is to, by looking at the question, retrieve the important information. So that means that as you read, you scribble down the key pieces of information given, typically the values that have been given and what they stand for. So for example, the 0.85 seconds there is referring to the time it takes. So that's the reaction time, Sama's reaction time. The other thing we want to take note of is the speed of the car, which is 82 kilometers per hour. So retrieve the useful information that will then help us solve the question, right? Number 4, we want to settle on the right method to use. So in this question here, we're being asked to find the distance, we've been given time, and we've been given speed. So this is the question about the question relating distance. We need the formula relating distance, speed, and time. Distance is speed times time, or speed is distance over time. That is the formula that we need. And so as you read the question carefully, you must think about the right formula or the right approach to solving the problem, okay? Number 5, we must communicate our solution. So set out the solution in clear steps. That means solve the problem in steps so that whoever is reading your work is able to follow your reasoning clearly, right? And lastly, once you come up with an answer, you want to check to ensure that your answer makes sense in relation to the problem or the question being asked, right? So for example, we're being asked here to find distance traveled within this reaction time. So when you slow down your car, do you think you'd travel 2 kilometers before the car stops? If you get answers like 2 kilometers, you must know that your answer is wrong. So check your answer to ensure that the answer makes sense. It's not possible that you can step on your brakes and it takes 2 kilometers before you stop. Also, it can't be 2 millimeters. You can't stop in 2 millimeters if your car is traveling at 82 kilometers per hour. So your answer must make sense relative to the question that is being asked. Okay? All right. So let's look at this very question to explain what we are saying. All right? Here's the example one more time. So Sama's reaction time when driving was measured to be 0.85 seconds. How far would her car travel in this time if the speed is 82 kilometers per hour? All right. So the first thing I note, of course, is that we are being asked for reaction time. So as a student, you must know what that means. What is reaction time? So look at the as you read the question, do you understand what the question is talking about? What is reaction time? And when it says, how far would her car travel, what is that asking for? So what does it mean, how far? Okay, so let's see. So reaction time refers to the time between seeing something and taking action. So for example, if you are driving and say an animal passes in front of you, there is that moment when you first see the animal, and then the information goes to your brain so as to decide to step on the brake. So the time between seeing the animal and actually stepping on the brakes is referred to as reaction time. Some people will take longer between seeing and actually stepping on the brake, and therefore they might cause an accident, collide with the animal. And some people are very, very good reaction time, so they will see and react very quickly, and so they may avoid colliding with the animal. So the reaction time refers to the time between seeing and taking action such as stepping on the brake. Okay? And then the question is talking about how far. Some people do not understand when it says how far. So how far in this case is referring to the distance that is traveled. All right? How far does this fellow travel? How far does the car travel before it comes to a complete stop? All right, so now we know what the question is asking for. We know the information that has been given. Time is 0.85 seconds. Speed is in kilometers per hour. So we should be able to find this. The formula we need is, of course, that distance is speed times time. Now we notice that speed is given in kilometers per hour while the time is in seconds. So when we calculate distance, it must either be in meters or in kilometers. But if we want our distance in meters, then the speed has to be in meters per second and the time has to be in seconds. So if we can maintain time in seconds, but we would need to change the speed to meters per second so that it conforms with the time in seconds, so that the units conform, right? Second and second. Alternatively, we can find the distance in kilometers, in which case the speed would have to be in kilometers per hour, which is 82, but we would then have to change our time into hours. So instead of time in seconds, we would need to change that from seconds to hours. Now, but which is the better deal? Changing to kilometers per hour would imply that we expect the distance traveled by the car to be in kilometers. We can find it in kilometers, but does it really make sense? When you step on the brakes, the car is hardly likely to travel kilometers. So in that, because of that, it is better to actually change into meters per second, because the distance you are bound to travel is probably going to be 10, 20, 30 meters instead of, it's not going to be a kilometer. All right, so because of that, I am changing speed into meters per second so that the distance is calculated in meters. This is not to say that calculating the distance in kilometers would be wrong. It is just not reasonable to leave your answer in kilometers when the distance is going to be way, way smaller than a kilometer, right? 30 meters, 20 meters, 25 meters, something like that is hardly close to the kilometer, and therefore does not warrant calculating that distance in kilometers. All right? All right, assuming that is clear, now we move ahead. So the first thing is to change the speed there from kilometers per hour, 82 kilometers per hour, to meters per second. And to do that, we will say V there for speed. The symbol we use for speed is V, V for velocity. We don't want to use letter S because letter S is used for something else. So we will use V, which means velocity, which is another name for speed. So the speed of the car is 82 kilometers per hour. To change that into meters per second, we are going to multiply by 0.27 recurring. You might be wondering how I got that, but that is exactly where the idea of rates is going to come in. So we multiply by 0.27 recurring, and we will get that the speed is actually 22.78. It's 77 recurring. We can say 23 meters per second if you like, or 22.8 meters per second. That is the speed in meters per second, right? The time we already have, which has been given to us in seconds, so we have everything we need to find the distance this car is going to travel. So then the distance traveled has to be speed times time. Speed is 22.78 meters per second, and the time is 0.85 seconds, and if we multiply that together, we will get the distance to be 19.36 meters. So this car, Summer's car, is going to travel 19.36 meters between her seeing something and actually stepping on the brake. All right, so if her reaction time is 0.85 seconds and she's traveling at 82 kilometers per hour, if she steps on the brake or in the duration of her reaction time before she steps on the brake, the car will have traveled 19.36 meters. Okay, like that. The question is, where am I getting 0.27 recurring? Where is that coming from? That is in fact the idea of rates that I want us to discuss. So let's see. Here is what we mean by rates. So in solving the previous question, we have introduced the idea of unit rate without actually mentioning it. Well, I did mention that it is rate. Let's see how that comes about, right? We change the speed from 82 kilometers per hour to 22 meters per second, so that the speed matches, the unit of the speed matches the unit of the time in seconds before we multiply speed and time. Okay, we could also have kept the speed in kilometers per hour, but in that case we would have had to change the time into hours as well. So how do I get that? Well, 1 kilometer per hour is the same as 1 into a kilometer is 1,000 meters. So we change from kilometers there to meters, so that's 1,000 meters. And from hours to seconds, 1 hour is 60 minutes, and 1 minute is 60 seconds. So 1 hour is the same as 60 times 60 seconds, and that's how we end up with 3,600 at the bottom. So we can reduce this to 1 over 3.6, or effectively, if you take 1,000 and divide by 3,600, you will get 0.27 recurring. Okay? So this is what gives us 1 over 3.6. So to change from kilometers per hour to meters per second, all we have to do is divide by 3.6. We can look at it that way. The alternative way to look at it is to find out the value of 1 over 3.6, and that is 0.277 recurring. So we can change from kilometers per hour by dividing by 3.6, right? Or by multiplying by 0.2777 recurring, like that. Okay. In other words, 1 kilometer per hour is the same as 0.277 meters every second, and I'm interested in that every second, per second. Okay, 1 kilometer per hour is equivalent to 0.27 meters per second, like that. Now let's use this to solve some questions, but before that we can define what rate really is. If two quantities x and y are directly correlated, so that an increase of one results in an increase of the other, we say they are directly related or directly correlated, then the value y when x is 1 is called the unit rate of y with respect to x. Okay? The value of y when the value of x is 1 is called the unit rate of y. All right? In other words, the value of y when x is equal to 1. All right? Here is what I'm talking about. So when we say directly correlated, we mean that as x increases, y also increases, so that if we were to draw a graph between them, it would be a straight line graph like that passes through the origin. We say the two are directly related, that x or y is directly related to x like that. Okay, so the value of y when the value of x is 1, there like that. What's the value of y when x is 1? That would be the unit rate. Another way of determining the unit rate, of course, would be to simply find the gradient of this line. And at this stage, all of us know how to find the gradient of a straight line. Okay? So the line needs to pass through the origin for them to be directly related or directly correlated. Okay? Here is what we are talking about. That is the rate of y relative to x. Relative to x is the value of y for a unit value of x. We are going to look at examples right now. Okay. Here's some examples of rates. An apple costs $4.60 per kilogram. In other words, for every kilogram, so $4.60 or $4.60 for every kilogram. So the denominator has to be 1. For the value of the numerator when the denominator is 1 is called the unit rate. Okay, so $4.6 per kilogram for every kilogram. Somebody earning 15 euro, 15.6 euros every hour. So the hour is sometimes called the hourly rate. So when the numerator is 15 euro, the denominator is 1 hour. So we call that the hourly rate of wage. Another example, currently diesel prices are in Sweden are about 28.2 Swedish krona per liter. Right? So for every liter, you pay 28 krona and 20 cents. So these are referred to as unit rate. So the cost per liter. Okay? The pay or the wage per hour. Okay? So the denominator is 1. All right? A rate is therefore defined as the unit value comparison of two quantities of different types. Now it's important that we remember that the two quantities we are relating must be of different types if we are talking about rate. I prefer to look at examples. All right, so when we say rate, we are basically thinking about how many for one. So how much do I get for 1 hour? What is the cost of tomatoes per kilogram and so on. Right? The value for 1. Here's an example or some examples. To travel 100 kilometers, a car requires 5 liters of petrol. What is the fuel consumption rate in kilometers per hour? How many kilometers per liter? Okay, so the fuel consumption rate in kilometers for every liter, for 1 liter, and in liters for every kilometer, per kilometer. Right, so to do this, how many in kilometers per liter? So that means that the term per there means divide by. So kilometers divide by liter. So we go up there and we want kilometers to be in the numerator and liters to be in the denominator, like this. So to answer this question, we will have to say for part A, it is kilometers per liter. So the kilometers goes to the numerator and the liters go to the denominator. And we have to write 100 kilometers for 5 liters. So 100 kilometers if you have 5 liters. So how many kilometers if I have 1 liter? That's what we are looking for. And that would be referred to as the unit rate. All right, so to do so, of course, just take 100 divided by 5, we will get 20. So therefore, 20 kilometers for every liter. So 20 kilometers for 1 liter, like that. We can conclude then So it's important that what we are trying to do is to ensure the denominator is always 1, because a rate is the unit value comparison of two quantities of different types. Okay, so that means how many for 1. So we can therefore say we get 20 kilometers for every liter of fuel that we spend. Okay, part B, we are now talking about liters per kilometer. So in this case now, liters must be in the numerator and kilometers must be in the denominator, because we want to see for 1 kilometer in the denominator, right? So 5 liters for 100 kilometers. So how many liters do we need for every kilometer? You just divide 5 by 100 and we get 0.05 liters for every kilometer that we travel. All right, we say that for every kilometer that we travel, we're going to make use of 0.05 liters. Okay, hope that makes sense. We move on. Here are some solved problems. Some of them I will solve, the others I will give answers, and I'll expect you to try them out. A 20 kilogram box of tomatoes is sold for 12 euros. Okay, what is the cost per kilogram? So divide by kilogram, we want the cost of 1 kilogram, right? So that we want the unit cost, right? B, how much will 8 kilograms of tomatoes cost? And C, how many kilograms of tomatoes does one get if one has got 9 euros? Okay, so let's see. So for part A, we want the cost per kilogram. So cost, we have to put the money in the numerator and the mass in the denominator, or the kilogram in the denominator. So we must say 12 euros for 20 kilograms. So 12 divided by 20. If we do that division, we get 0.6 euros per kilogram. So every kilogram costs us 0.6 euros or 60 cents. Okay. And that is sometimes called the unit rate or the unit cost in this case, right? So if we know the unit cost or the unit rate, then it is possible to find any other number of kilograms. So in other words, 1 kilogram will cost us this much. So how much does 8 kilogram cost us? It's important we know the cost of 1, so then we can find the cost of 2 kilograms, the cost of 3 kilograms. So if 1 kilogram costs this much, then 2 kilograms must be 0.6 times 2, 5 kilograms must be 0.6 times 5, and so on. 100 kilograms must be 0.6 times 100, and so on. So how many kilograms, how much will 8 kilograms of tomatoes cost? Well, 1 kilogram costs 0.6, so 8 kilogram must cost 0.6 multiplied by 8, like this. All right? So we know that the tomatoes will cost 0.6 euros per kilogram. So part B, if we're going to find the cost of 8 kilogram, we must take the unit cost and multiply by the number of kilograms we want to purchase, right? And that means take the 8 kilogram and multiply by the unit cost. So 0.6 multiplied by 8, and that gives us 4.8 euro. So we need to have 4.8 euro in order to buy 8 kilograms of tomatoes. Okay. Part C asks, how many kilograms of tomatoes does one get for 9 euros? So we need to know how many tomatoes we get per euro. Okay, how many tomatoes do we need to get the unit or the rate, unit rate for a euro? How many tomatoes can we get for 1 euro? And so then we are able to find the number of tomatoes we'll get for 9 euros. So what is the unit rate in number of tomatoes per euro? Well, we need to calculate a rate in kilograms per euro. And to do that, we must take the number of tomatoes, amount of tomatoes in kilogram divided by euro. So euros now in the denominator. And we have 20 kilograms for 12 euros. So how many kilograms per euro? We get 1.6 recurring kilograms for every euro that we spend, right? So if we know the cost per euro, then we can tell how many we are going, if we know the mass per euro, then we can tell how many kilograms we are going to get if we have 9 euros by just multiplying our unit rate by 9 euros. All right, so we can say 1 euro gives us 1.6 recurring kilograms. So 9 euros must be 1.6 multiplied by 9 euros, and that gives us 15 kilograms, like that. Okay, I hope this is clear. Let me know if you need additional help. Solve problem number 2. In this case, I think I've given you the solution, just the answer instead of solving in steps. So I want you to try answering these questions in the same kind of steps as I have done. So the average teenager complains about 13 things every 4 minutes. And this is on average. So there are those who complain more number of times per minute, and there are those who complain less, but the average is 13 different things every 4 minutes. How many things will he or she complain about in 24 minutes? Okay, you can pause the video and try this question out. Let's see how many things a teenager is going to complain about in 24 minutes. Well, if you've done this correctly, your answer should be 78 things. So in 24 minutes, an average teenager will have complained about 78 different things. All right? Very funny. Here's the next problem. Andy drove 1,200 kilometers in 12 hours. How far could he drive in 3 hours? So if he can drive 12 kilometers in 12 hours, how far does he travel in 3 hours? Again, pause the video and try the question out, and let's see what you get. If you've done it correctly, your answer should be 300 kilometers. So if he is able to travel 1,200 kilometers in 12 hours, then in 3 hours, Andy is going to do 300 kilometers. Right? Straightforward. Here is problem number 4. The table below shows the world population in 1990 and in 2013. We are assuming that the population increases at a constant rate. That means the number of people increasing every year is constant, right? Of course, this is not always the case. This is not normally the case. So let's see, if we assume that the rate of increase is constant, the amount by which the population increases every year is constant, the question is, so that's the table there, find the world's annual population growth rate. So what is this number of in increase per year if we assume that it is constant? All right? Well, to answer the question, we need to know by how much the population increased between 1990 and 2013, and we need to know how many years those are. Okay? So, same problem. So the population growth in the period 1990 to 2013 must be the population in 2013 minus the population in 1990, and that, if you subtract 7,095,217,980 subtract 5,306,420,000. If you subtract that, that is what we get. Okay, 1,788,792,980. So that's going to be the amount by which the population increased in a time duration which I think is 23 years. Yes. Okay. And so if we're going to find the rate of population growth, how many people per year, that means the number of years is in the denominator, so we have to take the population increase, divide by the time, and we will get, all right, 1.7 billion divided by 23 years, and if we do that calculation, I get 77,781 point something, so 782 people per year. And this is the annual growth rate. Okay? In reality, of course, the population does not increase or decrease at a constant rate. All right? 1 year is less, the next year is slightly more, and the number increases. In the future, we are going to look at more sophisticated ways of getting the population growth rate. But for now, this is sufficient to explain what we are discussing here as rate. Okay? Here is another problem related to speed and units. How far has a bus traveled if it goes at 54 kilometers per hour for a time of 40 minutes? So how far does this car travel? All right, guys, remember the issue here is reading a question, understanding it, designing a way to solve it, solving it in clear steps that anyone reading your question or reading your solutions can understand, and then checking back your answers to be sure that it makes sense in relation to the question being asked. All right, so what do you get for that? Question 2, which is faster? A cheetah running at a speed of 90 kilometers per hour or an eagle flying at 26 meters per second, right? That requires to either change 90 kilometers per hour into meters per second or 26 meters per second into kilometers per hour. To change this into 90 kilometers per hour into meters per second, you need to multiply by 0.27 recurring, right? 0.27777 like that. To change this, you need to actually divide by that same number. Okay? Number 3, the Earth travels a distance of 940 million kilometers around the Sun in 1 year. Find the speed of the Earth in kilometers per hour. Okay? Try these questions. I have given the answers, so check if the answers you get are the same as what I have here. So for the first one there, if you have done this correctly, you should find that in 40 minutes, the bus will have traveled 36 kilometers. For question number 2, all right, which one is faster? Well, if you check, 90 kilometers per hour is equivalent to 25 meters per second, and therefore, if you check that out, which one there is faster should be clear. Number 3, if you've done this correctly, you should find that the Earth is traveling at about 107,306 kilometers every hour on its way or on its orbit around the Sun. All right? Hope that is clear. Try them out and let's see if you're getting those answers. Again, remember to organize your solution in a way that anyone else reading your answers is able to follow. Okay? Here's a problem about currencies, currency conversion and currency rates. I have not solved this problem, so it is for you to try it out and let me know how you're doing. Okay, use the exchange rate table to answer the questions that follow. So this was an exchange rate table, I think about 2-3 years back. Things have changed, not 2-3, about 10 years back. Things have changed a bit, and so this may not be the exchange rate today, for example. All right, so here is an exchange rate table. US dollar to a number of international currencies. There is the euro, the pound, British pound, the Indian rupee, the Australian dollar, the New Zealand dollar, Singaporean dollar, and the Japanese yen. Okay, so these are values. Now, these are called exchange multipliers, or better still, you'd refer to this as rates. So rates from US dollars. So 1 US dollar will give you this number of euros. Okay, so this is to say euro is on the top, the dollar is in the denominator, right? On this side, when you're exchanging from euro to dollars, right, how many do you get in dollars? So euro is in the bottom, dollar is at the top. Okay, yeah, so if you're changing money to dollars and you have, say, 50 euros, then you multiply by this to get the number of dollars. Okay, if you're changing from US dollars to euros, so you have 50 US dollars, then you multiply by this here to get the number of euros, like that. Okay, so given that information, yeah, you can always scroll back to see the table. We want to answer the following questions. How much money in New Zealand dollars, how much money is 260 New Zealand dollars in USD? So in other words, convert this amount of New Zealand dollars to United States dollars. Okay? How much money? We are now changing Indian rupees, 38,000 Indian rupees to Singapore dollars. Here we are changing 300 United States dollars to Japanese yen. So how many Japanese yen do we get for 300 US dollars? Okay, and number 4, use the table to determine which of these currencies amounts exchange for the largest amount in USD. Okay, so in other words, take these values, convert them to USD, and see which one gets you the largest amount in USD. Right, so New Zealand dollars. Okay, so given those 5 figures, change each of them to USD and determine which one is the largest, gives you the largest amount of USDs. Okay, I guess that brings us to the end of part 1 of this discussion on rates. Again, remember, we are reviewing the key concepts as we move on. I'll see you in the next video. Let me know if you need some help with the discussion we've just had. All right? Thank you very much. See you in the next part.